Hey everyone, so we've got a pretty cool mathematical lesson today about similar right triangles. So here's an image where you've got a right triangle kind of sitting on its hypotenuse. It's a large right triangle, and what has happened here is we have drawn its altitude. So just vocabulary, this segment right here is known as the altitude because it measures how tall the triangle is when it's sitting on a base. Right? And so we want to find the length x of this altitude. So a couple things to discover is that what really happens when you draw this altitude is we end up having not just one large triangle, but we actually have a second triangle right here and a third triangle right here, right? So we have a total, and if with the first triangle being the large outline of it, but we have 3 total right triangles, and you can see that all 3 of them are actually right triangles. All right. Now, something else really cool happens. Not only do you have 3 right triangles, but according to a theorem, if we draw this altitude, then we're going to break this up into a total of 3 similar right triangles. All right, it's going to be a total of 3 similar right triangles. Therefore, this little guy right here is going to be similar to this big guy right here, which is similar to the larger one of the 3. So that's really cool. All right, now let's get busy. Let's actually try to find this value x. So we can say, all right, so if I think of this as the short side, and it's proportion to the long side, and I call them I can call them bases. This AB would be the hypotenuse, though. So 3 is to x as well. I can say the short side of this second triangle, so x, over the longer side, which is 12. And by now you should know that we can cross multiply and get x squared equals 36. Take the square root of both sides, and I get x equals 6. So 6 is the length of this segment. All right. And that's pretty cool. After that, if we want to, we can find the hypotenuse, all right, for either of these. And we can do that through Pythagorean theorem. So we can say 3 squared plus 6 squared, for example, to find AB equals the length of AB squared. All right, so we can say that 45 equals that side AB squared. So I can take the square root of both sides. So the square root of 45 is the length of AB. All right, length of AB, square root of 45. We can notice that's never-ending decimal. That's 6.70. A lot of decimals repeating. So what we do is we break this radical down. All right, and you can look at the notes for this process. We can break the square root of 45 into the square root of 9 times the square root of 5, because the square root of 9 is a perfect square. And so we can simplify that to 3 root 5. So this guy is 3 root 5. All right, I don't have to do Pythagorean theorem again to find this hypotenuse. It's the hypotenuse of the second triangle. Instead, I can think, well, this is the short leg, this is the long leg. The relationship is the short leg is half the size of the long leg, meaning that this guy is going to have to be 6 square roots of 5. All right. One other significant thing, there's many significant relationships right here. But one other significant thing is that there's a corollary. All right. There's a corollary that states that this height, 6, is actually always going to be equal to the geometric mean of 3 and 12. So what does the geometric mean? It's kind of like finding an average. You take 3, you multiply it by 12, and you take the square root of it. So 3 times 12 is 36, and the square root of 36 equals 6. That's a pretty easy way to find this value 6, all right? All right, so once again, that's because the length of the altitude of a hypotenuse of a right triangle is the geometric mean of those individual segments. There's one more corollary, all sorts of relationships here. It says the length of the leg of a right triangle is the geometric mean of the length of the hypotenuse in the segment. All right, that means that if we want to find this guy, we can actually just say, well, the hypotenuse measures 15. The segment adjacent to question mark measures 3. So if I take the geometric mean of that, I get the square root of 45, or square root of 9 times the square root of 5, or 3 root 5, which I had found a while ago. That works as well. Crazy.